4 billion miles of evidence, stretching behind 3I Atlas like a cosmic breadcrumb trail that shouldn't exist. When astronomers first detected it in the final days of October 2025, they thought it was routine. Another comet tail, another stream of sublimating gas catching sunlight as it drifted through the void. The champagne was nearly uncorked. Within 48 hours, the celebration turned to confusion, then to something that felt uncomfortably close to alarm. The spectroscopic signature was wrong. The particle density was impossible, and the wake wasn't behaving like any comet tail in recorded history. What they found instead has no name in our physics textbooks, no comfortable box to file it away in. And it's still out there right now, drifting somewhere between Mars and Jupiter, a 4 billion mile question mark. Written in matter we don't fully understand, waiting to tell us something we're not ready to hear. If this mystery has grabbed you the way it's grabbed the astronomical community, make sure to hit that subscribe button and turn on notifications, because this story is unfolding in real time and the next piece of data could change everything. Drop a comment with where you're watching from, what time it is there right now, and whether you think this wake is natural or something else entirely. And if you want to help this community grow so we can keep bringing you these stories as they break, share this video on X, on Reddit, in your Discord servers, anywhere people are asking the big questions about what's really out there. You're the reason we can chase stories like this, so thank you for being here. October 28th, 2025. Pan-STARRS telescope array in Hawaii, running its routine nightly sweep of the sky, flagging anything that moves against the background stars. An automated algorithm caught something unusual in the data stream. A fuzzy elongation extending from 3I Atlas, the interstellar comet discovered back in July that's been under intensive observation ever since. At first glance, it looked exactly like what you'd expect. A developing tail as the object continued its hyperbolic trajectory through our solar system. The discoverer, a graduate student named Sarah Chen at the University of Hawaii, sent the data through the standard pipeline, calculated preliminary photometry, and prepared what should have been a routine circular to the minor planet center. Just another data point on an already fascinating object. Nothing that would keep anyone awake at night. But Sarah Chen did something that changed everything. She didn't just process the images and move on. She looked at them. Really looked at them, and something bothered her about the brightness distribution, about the way the light fell off with distance from the nucleus. It was too sharp, too defined. Gas tails don't have edges. They diffuse into space, fading gradually as density drops and solar wind disperses the molecules across millions of miles. This thing had boundaries, so she requested follow-up observations, burning precious telescope time on what her advisor initially dismissed as a junior researcher being overly cautious. October 30th, Hubble Space Telescope, already scheduled to observe 3I Atlas as part of an ongoing campaign to characterize interstellar objects, turned its Wide Field Camera 3 toward the target. The images came down from orbit, were processed through the standard reduction pipeline, and landed on screens at the Space Telescope Science Institute in Baltimore. Within an hour, the room had gone quiet. Within 3 hours, senior staff were being called at home. The wake wasn't just visible, it was structured. Parallel striations running its entire length. Defined edges where the particles abruptly dropped off. Brightness clumps spaced at regular intervals like beads on a string. This was not a diffuse gas tail responding to solar wind pressure. This was something else. October 31st, Halloween. Astronomers worldwide probably found the date grimly appropriate as preliminary spectroscopic analysis came back from Hubble's Space Telescope imaging spectrograph. The spectrum that should have shown strong emission lines from water vapor, carbon dioxide, carbon monoxide, all the usual suspects you find when comet ices sublimate, was nearly blank. The emission lines were there, technically, but so weak they were barely above background noise. What dominated instead was continuum emission, reflected sunlight bouncing off solid particles. The spectrum of dust, not gas. But the particle density was orders of magnitude higher than any dust tail on record, and the wake extended 4.2 billion miles behind the object, a length that should be physically impossible to maintain without continuous active generation. The team lead, Dr. Michael Torres at Johns Hopkins, sent an email at 11:47 p.m. that night to his senior colleagues. The subject line read simply, "We have a problem." The body of the email contained 3 sentences. The 3I Atlas wake is not composed primarily of gas. Preliminary models suggest solid particles at densities 1,000 times higher than standard comet tails. I've requested emergency director's discretionary time on JWST for infrared follow-up. We need to understand what we're looking at before this goes public. It went public anyway. Amateur astronomers monitoring 3I Atlas, unbound by institutional caution or peer review protocols, had been taking their own observations and posting results to forums and social media. By the morning of November 1st, the astronomy corner of the internet was buzzing with speculation. The images were undeniable. The wake was real, extensive, and bizarre. And while professional astronomers carefully chose their words, unusual, requires further investigation, outside standard parameters, the amateurs were less restrained. The comments ranged from exotic ice chemistry to electromagnetic phenomena to the hypothesis that makes most scientists wince, but that absolutely has to be mentioned because intellectual honesty demands it: artificial origin. November 1st and 2nd, James Webb Space Telescope, the most powerful infrared observatory ever built, received its emergency observation approval and turned its mirrors toward 3I Atlas. For 36 hours, its near-infrared spectrograph and near-infrared camera collected photons that had bounced off those mysterious particles. Photons carrying information about temperature, composition, and molecular structure. The preliminary data started flowing back to Earth on November 3rd. The temperature measurements came first, and they made no sense. The wake was measuring 190 to 200 degrees Celsius. That's colder than it should be at that distance from the sun by 20 to 30 degrees. Objects in space reach thermal equilibrium with sunlight. They absorb radiation, heat up, and re-radiate in the infrared until they hit a stable temperature. These particles were too cold, as if something was actively cooling them, or they'd been formed so recently they hadn't warmed up yet. Neither explanation fit the timeline or the observed persistence. The spectroscopic data was even more confounding. JWST can identify molecules by their unique infrared fingerprints, the specific wavelengths where different chemical bonds absorb and emit radiation. It's an incredibly powerful technique that's allowed us to identify molecules in distant galaxies, in the atmospheres of exoplanets, in the cold reaches of interstellar space. When the spectroscopists ran the 3I Atlas wake data through their analysis software, comparing the observed spectrum against vast libraries of laboratory measurements, they got matches for about 27% of the features. Water ice, weakly present. Carbon dioxide ice, also weak. Carbon monoxide, moderate signal. And then, nothing. The remaining 73% of the spectroscopic features didn't match anything in the database. Not closely, not even approximately. 3 absorption bands at 486, 523, and 671 nanometers with no known molecular source. Infrared emission features at wavelengths that didn't correspond to any common ice or organic molecule. We're looking at chemistry that doesn't exist in our solar system, Dr. Torres told his team during an emergency video conference on November 4th. This material formed around a different star, under different conditions, with different elemental abundances. We don't have laboratory reference spectra because we've never made these molecules on Earth. We're effectively trying to identify a language we've never encountered before, with only partial dictionaries from related dialects. The numbers painted an impossible picture. The wake stretched 4.2 billion miles from nucleus to trailing edge. That's roughly the distance from the Sun to Neptune. It had maintained coherent structure for at least 4 months, ever since 3I Atlas had been bright enough for detailed observation. The estimated particle density, calculated from brightness measurements and scattering models, suggested between 100,000 and 500,000 particles per cubic meter in the densest regions. For comparison, a typical gas comet tail has maybe 1,000 particles per cubic meter, and that dissipates within days as solar wind tears it apart. These particles were staying together, maintaining formation, resisting the dispersion that should have scattered them across the solar system by now. And then there was the mass problem. If you calculate how much material must be in that wake, given its brightness and estimated density, you arrive at a figure around 10 to 15 million tons. Now calculate how fast 3I Atlas would need to be losing material to generate that much mass over 6 months, the duration since its discovery in July. The answer is approximately 1,000 tons per second. The estimated size of the nucleus is 5 to 7 kilometers in diameter. Even assuming it's a loosely packed rubble pile with the density of a snowbank rather than solid ice, it simply doesn't have enough mass to sustain that loss rate. At 1,000 tons per second, the entire object should have vaporized by now. It should be gone. Instead, brightness measurements show the nucleus maintaining constant luminosity, implying no catastrophic mass loss, no fragmentation, no death spiral. It's still there, apparently intact, trailing behind it 4 billion miles of material that by all rights shouldn't exist. 3 independent observatories verified the observations: Gemini Observatory in Chile, Keck Observatory in Hawaii, and the European Southern Observatory's Very Large Telescope in Chile all confirmed the wake's structure, its spectroscopic anomalies, its impossible persistence. This wasn't instrument error. It wasn't a processing artifact. It wasn't a misidentification of some foreground or background object. The wake was real. And with each passing day of data analysis, it became clearer that standard comet physics couldn't explain it. The preliminary models started coming back with error bars wider than the predictions themselves. The equations refused to cooperate. Something fundamental was missing from the physics, or 3I Atlas was doing something comets aren't supposed to do. By November 5th, a quiet alarm was rippling through the global astronomical community. The European Space Agency convened an emergency teleconference with planetary scientists from member nations. NASA's Planetary Defense Coordination Office received a classified briefing, not because anyone thought the wake was dangerous, but because unexplained phenomena in near-Earth space fall under their purview. The phrases showing up in private emails between researchers were carefully chosen but unmistakable in their implications. Outside standard, models, warrants comprehensive investigation, no clear mechanism identified, and one phrase that appeared in 3 separate communications from senior scientists who'd spent their entire careers studying comets. I've never seen anything like this. Here's where we need to pause and acknowledge what's happening. Because right now, in early November 2025, we're standing at one of those rare moments in science where the observations have outpaced the theory, where the data is screaming at us that something doesn't fit, that the boxes we've built to categorize cosmic phenomena aren't quite the right shape for what we're seeing. These moments are uncomfortable. They're exciting, yes, but they're also deeply unsettling because they force us to admit that our understanding is incomplete. And the question we're left with, the question that's keeping researchers awake as they run simulation after simulation trying to make the numbers work, is elegantly simple and terrifyingly complex. If that wake isn't made of gas, what is it made of? And how is it staying together? Let's start with what should be happening, because you can't understand why 3i Atlas is breaking the rules until you understand what the rules are. Comet tails are supposed to be simple. Beautiful, yes. Photogenic, absolutely. But simple. You have a chunk of ice and rock that spent most of its existence in the frozen outer reaches of a solar system, barely above absolute zero, completely inert. As it falls toward the sun, sunlight intensifies. Heat penetrates the surface. Ices that have been frozen for billions of years, water, carbon dioxide, carbon monoxide, methane, ammonia, begin to sublimate, transitioning directly from solid to gas without bothering with the liquid phase. The gas escapes from the nucleus carrying dust particles with it. The solar wind, that supersonic stream of charged particles constantly blowing out from the sun at 1,000,000 miles per hour, catches the gas and pushes it away from the sun, always away, creating the characteristic tail that always points in the anti-solar direction. This is first semester astronomy. This is textbook physics. Comets have been following these rules since we've been watching them, probably for billions of years before that. The gas dissipates quickly. Within days or at most weeks, solar wind and the vacuum of space tear apart the molecular clouds, spreading atoms across millions of miles until the density drops below detectable levels. The tail is constantly being replenished by fresh gas from the nucleus, but what's already been released doesn't stick around. It disperses, it fades, it disappears. This is why comet tails are dynamic, constantly changing as the balance between fresh gas production and dispersion shifts depending on the comet's distance from the sun. You can calculate the dissipation timescale using basic fluid dynamics and known solar wind parameters. For typical cometary gas at Earth's distance from the sun, you're looking at 2 to 3 days before the tail loses structural coherence. Maybe a week if conditions are particularly favorable and the gas is unusually dense. But not months, never months, and certainly not 4 months with no sign of dissipation while maintaining clear structural boundaries and internal organization. 3i Atlas looked at these rules, considered them carefully, and decided they were more like suggestions. The wake has been visible and structured since at least early July when the object was first discovered, possibly longer if we'd been watching. It's now November, 4 full months. The spectroscopy tells us it's not primarily gas. Those emission lines are too weak, too subdued. What we're seeing instead is reflected sunlight bouncing off solid particles. Dust, essentially, though calling it dust feels inadequate when 73% of its composition doesn't match anything we've encountered before. These particles should be responding to radiation pressure from sunlight, which pushes outward just like solar wind pushes on gas. They should be dispersing, spreading into a diffuse cloud. They should be following predictable trajectories that we can model with orbital mechanics and radiation transport equations. They're not. The wake follows 3i Atlas's trajectory almost exactly. Where the object has traveled, the wake extends behind it like a cosmic contrail. The angular deviation from the anti-solar direction, the direction pointing directly away from the sun where a normal tail would point, is approximately 67 degrees. 67 degrees off from where basic physics says it should be. You could argue that maybe these are extremely dense particles, massive enough that radiation pressure can't move them significantly, so they're just following ballistic trajectories after being ejected from the nucleus. Fine. Let's calculate what density would be required. The particles would need to be roughly 1,000 times denser than typical comet dust. We're talking about particles with the density of solid rock or metal, not fluffy ice dust aggregates. But if they're that dense they're not sublimating off the surface, you'd need mechanical ejection, violent enough to throw rock-density particles at escape velocity from a 5-kilometer nucleus. That requires energy. A lot of energy. And there's no observed mechanism providing that energy. Here's another problem. The wake has internal structure. This is what made Sarah Chen look twice at those first Pan-STARRS images, what made the Hubble observers immediately escalate to senior staff. When you zoom in on high-resolution images of the wake, you don't see a uniform distribution of particles. You see organization. Parallel lanes running the length of the structure, 7 to 9 distinct striations, visible in enhanced contrast processing. Each lane is roughly 50,000 miles wide, separated from its neighbors by 80,000 to 100,000 miles. These lanes don't merge or disperse. They maintain their identity across billions of miles. Additionally, there are brightness clumps, concentrations of particles spaced at quasi-regular intervals of 200 to 300 million miles. 12 to 15 distinct clumps visible in the longest exposures, each one brighter than the surrounding wake material, each one suggesting a discrete ejection event or pulsed release of material. This kind of structure doesn't happen in nature. Not without cause, not without mechanism. The striations could potentially be explained if 3I Atlas has a strong magnetic field and the particles are charged, aligning along field lines like iron filings near a magnet. But comets don't typically have strong magnetic fields. They're too small to maintain a molten metallic core like Earth's dynamo. The charged particle hypothesis also requires that the particles remain ionized over 4 months, which means they'd need to be continuously exposed to UV radiation from the sun and continuously losing electrons. At the observed particle densities, collisions between particles should neutralize charges within hours or days, not months. The field lines would need to be extending billions of miles from the nucleus, which requires field strengths we've never measured in cometary bodies. The quasi-periodic clumping could suggest rotational effects. If the nucleus is spinning and has active regions that only face the sun at certain rotation phases, you might get pulsed ejection every few weeks. This is plausible. Some comets show outbursts correlated with rotation. But the regularity is suspicious. Most comets have irregular shapes and chaotic rotation, especially interstellar objects that haven't been tidally locked to any star. Getting periodic ejections spaced at 200-300 million mile intervals requires not just rotation, but stable rotation with active regions that stay active at the same intensity for months, and it still doesn't explain what those active regions are ejecting or how they're imparting enough velocity to particles to reach escape velocity. Now factor in the temperature problem that JWST revealed. The wake is 20 to 30 degrees colder than thermal equilibrium would predict. Objects in space at that distance from the sun, exposed to that much sunlight, should reach a predictable temperature where absorbed radiation equals emitted radiation. It's basic thermodynamics. The only ways to be colder than equilibrium are extremely high reflectivity, albedo approaching 1.0, meaning nearly perfect mirrors, or active cooling via endothermic processes, chemical reactions that absorb heat, or the particles were formed so recently they haven't thermalized yet. High albedo could work if the particles are fresh ice crystals with pristine surfaces, but fresh ice sublimates, which produces gas, which we're not seeing in the spectroscopy. Endothermic cooling requires ongoing chemical reactions, which means active chemistry happening in the particles right now. That's possible. Some complex organic molecules can absorb heat during phase transitions or structural rearrangements, but you'd expect to see spectroscopic signatures of those reactions, emission or absorption features corresponding to the excited molecular states. We're not seeing those either. The recently formed hypothesis is intriguing and deeply troubling. If the particles are continuously being created or refreshed somehow, that could explain both the cold temperature and the sustained density. Maybe material is being ejected from the nucleus, then undergoing some transformation in space. Condensation, polymerization, aggregation, that creates new particles that haven't had time to warm up yet. This is exotic but not impossible. We know that some molecules can polymerize in space when exposed to UV radiation, building long carbon chains from simpler precursors. If 3I Atlas is releasing volatile organics that then polymerize into solid particles in the wake, you could potentially get sustained production. But again, the spectroscopy should show this. We should see precursor molecules, we should see the intermediates, we should see signatures of the polymerization process. And we're not seeing any of that clearly enough to confirm the hypothesis. Let me give you a sense of how frustrated the modeling teams are right now. Dr. Elena Vorobyova at the Max Planck Institute for Solar System Research has been running simulations of cometary gas dynamics for 20 years. She's modeled Hale-Bopp, she's modeled 67P, Churyumov-Gerasimenko, that the Rosetta spacecraft visited. She's modeled dozens of Jupiter family comets. Her models work. They match observations. They predict tail structures with reasonable accuracy. When she tried to model 3I Atlas using standard parameters, gas production rate inferred from brightness, solar wind conditions measured by spacecraft, assumed composition based on spectroscopy, the models crashed. Not computational crashes, but physical crashes where the equations spit out nonsense. Negative densities, imaginary temperatures. The physics engine underneath the code was reporting that something violated conservation of energy. She tried adjusting parameters, widening uncertainties, testing extreme scenarios. Nothing worked unless she introduced ad hoc terms, unexplained forces acting on the particles, mysterious energy sources, parameters she had to tune by hand with no physical justification beyond this makes the model not crash. In a video call with colleagues on November 6th, she said something that's been circulating in private communication since. Either our understanding of cometary physics is fundamentally wrong, which seems unlikely, given centuries of observations, or this object is doing something no comet has done before. And I don't know which possibility disturbs me more. The density problem remains the most quantitatively troubling. 1,000 tons of material per second, sustained for 6 months, totaling 15 million tons. The nucleus is estimated at maybe 100 billion tons total mass, if you're generous with the density assumptions. Losing 15 million tons is 0.015% of the total mass. That's not catastrophic by itself. Objects can sustain that kind of mass loss, but the rate is what breaks the physics. To sublimate 1,000 tons per second, you need a surface area receiving enough solar energy to sublimate that much ice. At 3I Atlas's distance from the Sun when the wake was forming, it's been between 2 and 4 AU most of the observation period. Solar flux is about 340 to 85 watts per square meter, depending on exact distance. Water ice sublimates at roughly 2.8 million joules per kilogram. Do the math. To sublimate 1,000 tons per second requires 2.8 trillion watts of power. The total solar power hitting a 7-kilometer diameter sphere at 3 AU is about 4 billion watts. You're short by a factor of 700. Even if the entire surface was perfectly efficient at converting sunlight to sublimation, which is impossible, you can't get enough energy to sustain that mass loss rate, unless the material isn't coming from sublimation. Unless it's coming from fragmentation, mechanical erosion, some process that doesn't require heating ice. Fragmentation can eject material at high rates if something is actively breaking the object apart. But we'd see that. We'd see brightness changes as the nucleus crumbles. We'd see fragments separating, creating multiple objects. We'd see the signature of catastrophic disruption. And we're not. The nucleus appears stable, not fragmenting, not disintegrating, just trailing behind it this impossible wake of particles that shouldn't be there. The 3 working hypotheses that haven't been completely ruled out by observations are each uncomfortable in their own way. Hypothesis 1. Exotic ice chemistry. Maybe 3I Atlas contains molecular ices we've never encountered, with sublimation behaviors we can't predict because we've never synthesized them in laboratories. These hypothetical ices could sublimate at unexpected temperatures, could produce solid particles rather than gas, could somehow maintain structure through mechanisms we don't understand. This hypothesis is favored by most researchers because it requires the least revision to existing physics. It just requires that our chemical knowledge is incomplete, which is certainly true. But it feels like a catch-all, a way to label ignorance with a scientific-sounding name. Exotic ices is placeholder text for we don't know. Hypothesis 2, electromagnetic phenomena. The wake could be held together by plasma physics, with charged particles organizing along magnetic field lines or creating self-sustaining electromagnetic structures. Laboratory plasmas can form filaments, sheets, and bounded regions through collective electromagnetic effects. Scale those processes up to astronomical dimensions, and you might get something like what we're observing. This hypothesis has the advantage of explaining the structure, the defined edges, the persistence. Electromagnetic forces are strong enough to overcome dispersion, but it requires that 3I Atlas has properties we've never observed in comets. Sustained electrical charge generation, magnetic field topology that extends billions of miles, particle populations that maintain ionization over months. It's not impossible, but it's exotic, requiring confirmation of effects we're not sure are present. Hypothesis 3 is the one that appears in private conversations but rarely in official reports. Mechanical mass loss, but not from fragmentation. Instead from something actively organized, something that releases material in controlled ways, creating structure deliberately rather than accidentally. I need to be absolutely clear. There is zero evidence for artificial origin. None. Every observation has at least one potential natural explanation. But when you have multiple anomalies, structured wake, impossible density, cold temperature, unknown composition, quasi-periodic clumping, each individually explainable but collectively unusual, you start to wonder. Not because you want to, not because it's scientifically justified, but because the possibility sits there in the back of your mind whispering, what if? And that's where we are in early November 2025. Professional astronomers running models that don't work, amateurs posting observations that don't fit theory, and everyone waiting for the next piece of data that might either resolve the mystery with a mundane explanation or deepen it into something that requires rewriting textbooks. The wake remains out there, 4 billion miles of particles that shouldn't exist according to standard physics, carrying composition that doesn't match our libraries, exhibiting organization that has no clear mechanism, and 3I Atlas continues its hyperbolic trajectory through our solar system, indifferent to our confusion, leaving behind evidence that we're either missing something fundamental about how comets work, or facing something that isn't quite a comet at all. Every good mystery needs suspects, every anomaly demands explanation. And right now in early November 2025, we have 4 main interpretations for what's happening with 3I Atlas and its impossible wake. 4 ways to make sense of particles that persist when they should dissipate, structure where there should be chaos, cold temperatures where equilibrium should reign. One of these scenarios is safe, comfortable, the kind that lets astronomers sleep soundly knowing the universe still operates according to familiar rules. The other 3 progressively peel back layers of comfort, exposing possibilities that range from exotic to unsettling to the kind that makes you check the sky just a little more often. Let's walk through them one by one, examine what they predict, what they explain, and what they leave disturbingly unanswered. And you can decide which one feels most likely or most troubling. Scenario 1 is the Occam's razor option, the explanation requiring the fewest assumptions and the least violence to established physics. According to this view, the 3I Atlas wake is exactly what it appears to be at first glance: frozen material ejected from an interstellar comet. The twist is composition. This object didn't form in our solar system. It condensed from a protoplanetary disk around a different star, potentially one with elemental abundances unlike our sun's, certainly one with different temperatures and pressures during planet formation. The ices it contains might be molecules we've never synthesized on Earth because they require exotic formation conditions. Complex carbon compounds, polycyclic aromatic hydrocarbons forming intricate lattices, organic molecules with 30 or 40 atoms arranged in ways our chemistry textbooks don't describe because we've never had reason to create them. When these exotic ices sublimate under solar heating, they might not produce simple gases. Instead, they could form complex solid particles. Think of them as organic snowflakes or carbon soot aggregates. These particles would be heavier than gas molecules, more resistant to dispersion, capable of maintaining structure across longer timescales. The 73% unknown composition in the spectroscopy? That's the signature of these alien molecules, chemicals that formed in a stellar environment with different carbon to oxygen ratios, different nitrogen abundances, different trace element distributions. We can't identify them because our spectroscopic libraries were built from laboratory work replicating solar system conditions. We've literally never seen these molecules before because they don't exist naturally in our cosmic neighborhood. This explanation is intellectually satisfying because it requires no new physics, only incomplete chemistry. It acknowledges that the universe is vast and varied, that different stellar environments produce different chemical inventories, and that our knowledge has gaps. Research groups are already working on this angle. Dr. Yuki Tanaka at Kyoto University has been running quantum chemistry simulations trying to predict what molecules might form around stars with high carbon to oxygen ratios, the kind of ratios that spectroscopy suggests 3I Atlas's parent star might have had. Her preliminary results shared in a preprint posted November 7th show that you can get stable molecules with 50 or more. Atoms, complex organics that would produce solid particles when heated rather than simple gases. The spectroscopic signatures her models predict don't match 3I Atlas perfectly, but they're closer than anything else. Close enough to be encouraging. Close enough to be the explanation most peer-reviewed papers will likely cite. But there are cracks in this comfortable scenario. It explains composition, yes. It explains why the particles are solid rather than gas. But it struggles with the persistence. 4 months without significant dispersion is still unusual even for solid particles. It doesn't naturally explain the cold temperatures. Exotic organics should still thermalize with sunlight unless their albedo is impossibly high. And it really doesn't explain the structure, those parallel striations and defined edges. Exotic chemistry gives you exotic composition, but organization requires something more. Forces, mechanisms, something keeping particles aligned when they should be scattering randomly. You can wave your hands and invoke unique particle properties or electromagnetic effects from charged organics, but at that point you're stacking assumptions, moving away from Occam's razor toward something more elaborate. Scenario 2 embraces the mechanical and sidesteps the chemical. Forget sublimation entirely. What if 3I Atlas is fragmenting, not catastrophically all at once, but continuously through thermal stress or rotational forces? Interstellar objects entering the inner solar system experience dramatic temperature gradients. The surface heats while the interior remains frozen, creating expansion differentials, thermal cracking, mechanical failure. Each orbit segment subjects the nucleus to cycles of heating and cooling. The object spins, all comets do, and if it's spinning fast enough, centrifugal forces work against structural integrity. Combine rotation with thermal stress, and you get continuous shedding, small fragments constantly being peeled off like paint flaking from sun-damaged wood. These fragments would follow ballistic trajectories almost identical to the parent body's path. They're not being pushed by solar wind because they're solid and massive enough to resist radiation pressure. They're just following orbital mechanics, traveling along with 3I Atlas like a debris trail. The quasi-periodic clumping we observe, that correlates with rotation phase. Every time a particularly weak spot rotates into sunlight, thermal expansion triggers a microfragmentation event, ejecting a burst of material that shows up as a brightness clump. The striations could represent different source regions on the nucleus. Maybe the object has compositional heterogeneity, different zones shedding material with slightly different properties, and those differences create visible lanes in the wake. This scenario has appeal because fragmentation is common and well documented. Comet Shoemaker-Levy 9 famously broke into 20-plus fragments before hitting Jupiter in 1994. Comet Ison disintegrated approaching the Sun in 2013. Comet 73 Schwarzmann-Wachmann 3 has fragmented multiple times since 1995, creating spectacular debris clouds. The physics is understood. The mechanisms are proven. Extend that to continuous low-level fragmentation rather than catastrophic breakup, and you've got a plausible explanation. Dr. Naomi Aoki at MIT's Department of Earth, Atmospheric and Planetary Sciences published calculations on November 5th, showing that an object with 3I Atlas's estimated size and rotation period could sustain fragmentation rates matching the observed wake mass if its structural strength is low, essentially if it's barely held together, more rubble pile than solid body. But fragmentation has problems too. The big one is that we're not seeing it directly. Fragmentation events typically produce observable brightness changes as fresh surface gets exposed or as fragments separate, creating multiple light sources. 3I Atlas's brightness has remained remarkably stable. There's been no sudden outburst, no splitting event, no dramatic change that would indicate major structural failure. You could argue that continuous low-level fragmentation wouldn't produce detectable brightness changes because each individual event is small. Maybe. But over 4 months of sustained mass loss at the rates required to explain the wake, you'd expect some signature. Additionally, the spectroscopic composition problem persists. Mechanical fragmentation would eject material with the same composition as the nucleus surface, which should be water ice dominant in most comet models. Yet we're seeing that anomalous 73% unknown composition. Fragmentation doesn't create new chemistry, it just breaks up what's already there. Scenario 3 ventures into plasma physics territory, and this is where most astronomers start hedging their language with caveats because we're beyond well-tested mechanisms into active research frontiers. The hypothesis goes like this. As material sublimates from 3I Atlas, it doesn't just become neutral gas, it ionizes. Solar UV radiation strips electrons from atoms and molecules, creating a plasma, a gas of charged particles. These charged particles interact electromagnetically with each other and with the sun's magnetic field, which extends throughout the solar system. Under the right conditions, plasmas can self-organize, forming structures called filaments or current sheets where particles align along field lines. Laboratory plasmas do this routinely. It's the basis of plasma containment in fusion reactors. Scale these processes to astronomical dimensions and you might get organized structures like the striations we're observing. The wake particles could be dust grains that become electrically charged through a process called photoelectric effect. Sunlight knocks electrons off their surfaces. Charged dust behaves very differently from neutral dust. Electromagnetic forces between charged grains can be stronger than gravity or radiation pressure at small scales. These forces could bind particles together, creating structured clouds that resist dispersion. The defined edges of the wake could represent the boundary where electromagnetic forces balance dispersion forces. The cold temperature could result from particles being electrostatically levitated from the surface before they've thermalized. Imagine dust being lifted off the nucleus by electrical repulsion while still frozen, then never warming up because the density is high enough that particles shade each other from direct sunlight. This is exotic but not impossible. In fact, there's precedent for electromagnetic effects in comets. Comet Halley showed plasma tail disconnection events where the ion tail would detach and reform, driven by magnetic field interactions. The Rosetta spacecraft measured electrical fields around Comet 67P strong enough to levitate dust. The physics exists. The question is scale. Can you maintain electromagnetic structures across 4 billion miles? That requires either an incredibly strong magnetic field extending from the nucleus, which seems implausible for a small icy body, or self-sustaining plasma currents where the structure maintains itself through collective effects. Dr. Anthony Chen at UCLA has been modeling dusty plasma dynamics in cometary environments for a decade. In a preliminary analysis posted to arXiv on November 8th, he suggests that if 3I Atlas has unusually high dust production and that dust has specific charge-to-mass ratios, you could potentially get filamentary structures that persist longer than standard gas tails. His models produce wake-like features with some of the observed properties, but he's careful to note that the energy budget is tight and the conditions required are at the extreme edge of plausibility. And now we arrive at scenario 4, the one that makes scientists uncomfortable, but that intellectual honesty demands we at least articulate clearly before dismissing. What if the wake isn't natural? What if some component of what we're observing reflects deliberate organization rather than emergent physical processes? I need to hammer this home with absolute clarity. There is no evidence for artificial origin. None whatsoever. Every single observation has potential natural explanations. The spectroscopic anomalies could be exotic chemistry. The structure could be electromagnetic effects. The persistence could be unique particle properties. We are not claiming, suggesting, or even tentatively proposing that 3I Atlas or its wake is artificial. But the question exists whether we voice it or not, and pretending it doesn't exist is intellectual cowardice. So let's think it through as a rigorous exercise in distinguishing natural from artificial phenomena, because this skill matters for SETI, for future observations, for the day when we do encounter something genuinely artificial and need frameworks to recognize it. What would artificial organization look like? Precise geometric patterns, regular spacing, mathematical relationships, symmetries that natural processes rarely produce, information content, structure that encodes data like prime numbers or physical constants, energy signatures, power sources we don't recognize, thermal or electromagnetic emissions that don't match known processes, active modification, trajectories that deviate from pure gravitational paths in ways consistent with propulsion or maneuvering. Does 3I Atlas show any of these? The quasi-periodic clumping is suggestive of organization, but natural rotation can produce periodic effects. The parallel striations show structure, but plasma filaments or fragmentation from aligned surface features could explain that. The unknown composition is mysterious, but unknown just means we haven't identified it yet, not that it's artificial. There's no detected energy signature beyond what sunlight provides. There's been no confirmed trajectory deviation. Precise astrometry is still being compiled, but preliminary orbits show hyperbolic paths consistent with natural interstellar objects. On every quantitative measure, 3I Atlas looks natural, just unusual. The only reason Scenario 4 gets mentioned at all is the precedent of Oumuamua, which showed non-gravitational acceleration that sparked exactly this debate. Harvard astronomer Avi Loeb proposed it might be a light sail, an artificial structure pushed by radiation pressure. The astronomical community largely disagreed, favoring explanations involving hydrogen icebergs or unusual outgassing. The debate became acrimonious and is still unresolved. The lesson from Oumuamua isn't that artificial explanations are likely, they're not, but that we need clear frameworks for evaluating them, and we need to exhaustively eliminate natural possibilities before even considering alternatives. For 3I Atlas, we're nowhere near exhausting natural possibilities. We're still at the stage of identifying which natural processes are involved, not ruling them all out. So here's where Act 3 leaves us. 4 scenarios ranging from exotic but natural chemistry to mechanical processes, to electromagnetic plasma, to the uncomfortable question of artificial origin. The smart money is on scenario 1 or 2, probably some combination where exotic composition produces unusual fragmentation behavior. Scenario 3 is plausible but requires confirmation of electromagnetic effects we haven't definitively measured. Scenario 4 is speculative to the point of being unscientific with current evidence, mentioned only for completeness and as intellectual exercise. What we need to distinguish between these is more data, better observations, and time to let the EI now scientific process work. And some of that data is coming in right now, as November observations from multiple observatories start filling in details about what that wake actually looks like at the highest resolution we've ever achieved. October 31st through November 4th, 2025. Hubble Space Telescope dedicated 47 hours of observation time to 3I Atlas, an emergency allocation approved within 24 hours of the initial wake detection. That's extraordinary by Hubble's standards. Telescope time is precious, scheduled months in advance, fought over by astronomers worldwide. Getting directors' discretionary time requires demonstrating that the target is uniquely important and time-critical, that waiting for the normal proposal cycle would mean missing the opportunity. 3I Atlas qualified. An interstellar object displaying unprecedented behavior, potentially providing insights into galactic material exchange and exotic chemistry, observable only during this narrow window as it traverses our inner solar system. The Space Telescope Science Institute approved the request, bumped scheduled observations to later dates, and pointed Hubble's Wide Field Camera 3 and Space Telescope imaging spectrograph directly at the mystery. What came back was the highest resolution view of an interstellar object's wake ever captured, images where individual pixels represented roughly 300 kilometers of actual space. You could see structure that was completely invisible in ground-based observations, details that transformed the wake from a mysterious blur into something that demanded explanation. The parallel striations that Sarah Chen had first noticed in Pan-STARRS data resolved into distinct lanes, each one maintaining a width of approximately 50,000 miles, separated from neighbors by 80,000 to 100,000 miles of relatively empty space. 7 lanes visible clearly, possibly 9 if you counted fainter features that might be real structure or might be image artifacts at the noise limit. These lanes extended across the entire visible length of the wake. 4.2 billion miles of organized matter that showed no sign of merging, no erosion of boundaries, no diffusion that should have smeared them together over the 4 months they'd been forming. Dr. Sarah Millstone at the Space Telescope Science Institute, who led the Hubble observation campaign, described her reaction in a video call with the research team. "I've been working with Hubble data for 15 years. I've seen galaxies colliding, stars exploding, planetary nebulae in exquisite detail. I thought I was beyond being surprised by astronomical images, but when those first processed frames came through showing the wake structure, I just sat there staring at my monitor for probably 5 minutes trying to reconcile what I was seeing with what physics said should be there. Those lanes shouldn't exist. Particles don't spontaneously organize into parallel streams. They need a mechanism, a force, something shaping their distribution. And we don't know what that something is." The brightness clumps were even more dramatic in Hubble's view. 12 distinct concentrations of particles visible, spaced at intervals that varied between 180 and 320 million miles, but averaged around 240 million miles. Each clump was perhaps 20 to 30 million miles across, glowing brighter than the surrounding wake by factors of 2 to 5 depending on wavelength. The spacing suggested periodic release, something causing material to be ejected in bursts rather than continuously. If you assume the clumps represent individual ejection events, and you know the spacing between them and the object's velocity, 26 kilometers per second, you can calculate the time interval between events. The math gives you roughly 2 to 3 weeks, something happening on 3i Atlas every 2 to 3 weeks since at least July that pulses out a burst of particles. What causes periodic activity on that timescale? Rotation is the obvious first guess. If 3i Atlas rotates with a period of 2 to 3 weeks and has active regions that only eject material when facing the sun, you'd get periodic bursts. But 2 to 3 weeks is an unusually long rotation period for a comet. Most comets rotate every few hours to a few days. Long period rotation suggests either a very large object, which 3i Atlas might be at 5 to 7 kilometers, or an object that's been spun down by some process, maybe outgassing torque over millions of years. The Rosetta mission to Comet 67P measured how outgassing can alter rotation rates, speeding objects up or slowing them down depending on where the jets emanate. It's plausible that 3i Atlas has a weeks-long rotation period, but plausible isn't confirmed, and without direct measurement of the rotation, which requires either resolved imaging of surface features or light curve analysis over full rotation periods, we're speculating. The edges of the wake were perhaps the most disturbing feature in Hubble's data, not because of what they showed, but because of how sharp they were. In astrophysical context, sharp is relative. We're talking about transitions happening over distances of a few million miles. But for a comet tail that should diffuse into space over hundreds of millions of miles, a 5 million mile boundary is razor sharp. It's like finding a fence in interplanetary space, an invisible barrier that particles respect, beyond which they simply don't exist in significant numbers. The brightness drops by a factor of 10 across that boundary distance. Spectroscopically, the composition doesn't change appreciably. The unknown 73% is still unknown inside and outside the edge. The particles just stop being there. Containment implies force, something holding particles within bounds. Gravitational self-binding is too weak. The wake's mass is far too low and spread too thin for gravity to be relevant. Electromagnetic containment could work if the particles are charged and there's a magnetic field structure creating boundaries. Or the edge could represent not containment, but simply the trajectory limit. Particles ejected with a specific velocity distribution will spread only so far before their density drops below detection thresholds. But the sharpness argues against simple ballistic spreading, which should produce exponential fall-off profiles, not sharp cutoffs. Then came JWST's contribution. November 1st and 2nd, the near-infrared spectrograph collected photons that had interacted with wake particles, photons carrying information about temperature and composition that visible light observations can't provide. The temperature data hit first and made no sense for reasons already discussed, negative 190 to negative 200 Celsius, when equilibrium predictions said negative 160 to negative 170. But the composition data was the real revelation. JWST can see molecules that are invisible to optical telescopes, organic compounds with vibrational modes in the infrared, ices with characteristic absorption bands at specific wavelengths. The spectroscopists ran the data through automated identification software linking observed features to laboratory databases containing thousands of molecular spectra. Match rate, 27%. 27% is horrifyingly low for a confident identification. Normally you'd expect 80+% match for known materials, with the remainder being noise, minor contaminants, or unexpected but identifiable molecules once you dig deeper. 27% means most of what you're looking at isn't in the databases. The identified portion included weak water ice signatures at 3.0 and 6.0 microns, weak carbon dioxide ice at 4.3 microns, moderate carbon monoxide at 4.7 microns, all expected for a comet, all present but subdued. The remaining 73% showed features at wavelengths where nothing in the spectral library lived. Three particularly strong absorption bands at 5.2, 7.8, and 11.3 microns with no known molecular source. These weren't weak features hiding in noise. They were strong, unambiguous absorption dips that any molecule present in significant quantities would produce. Dr. Priya Kapoor at NASA Goddard, who specializes in infrared spectroscopy of solar system objects, has spent the last week comparing 3I Atlas spectra against every exotic molecule she can think of. Complex organics that form in Titan's atmosphere. Tholins produced in laboratory simulations of early Earth chemistry. Polycyclic aromatic hydrocarbons from interstellar dust. Amino acids, nucleobases, fullerenes, nothing fits. I'm running out of molecules, she told colleagues in an email that was shared more widely than probably intended. We've checked everything that should reasonably exist in a comet environment. Either this object contains molecules we've never synthesized, or there's something wrong with our spectroscopic interpretation, or the unknown material isn't molecular at all, but some kind of amorphous solid with unusual absorption properties. I'm hoping it's the first option because that would be scientifically exciting. If it's the third option, we're in truly uncharted territory. Comparison with other interstellar objects reveals how singular 3I Atlas is. Oumuamua, discovered October 2017, showed no detectable coma or tail whatsoever, despite spectroscopic searches. Its composition remains unknown because we never got spectra. It was detected only through reflected light, appearing as a point source even in Hubble images. What we know, highly elongated shape inferred from light curve variations, reddish color suggesting organic rich surface, non-gravitational acceleration suggesting some form of outgassing despite no visible coma. Oumuamua was weird through absence of features. 3I Atlas is weird through presence of features that don't make sense. 2I Borisov, discovered August 2019, was refreshingly normal. It showed strong water and carbon monoxide emission lines, developed a proper gas tail that pointed anti-solar, exhibited outgassing rates consistent with its brightness and estimated size. Spectroscopy matched solar system comets reasonably well, some compositional differences, higher carbon monoxide relative to water than typical, but within the range of variation we see among long-period comets from the Oort cloud. Borisov proved that not all interstellar objects are bizarre. Some are just comets that happened to form around other stars and got ejected through perfectly normal dynamical processes. 3I Atlas and Oumuamua are the outliers, and having 2 outliers out of 3 confirmed interstellar objects is statistically uncomfortable. It suggests either that most interstellar objects are weird and we got lucky that Borisov was normal, or that we're selectively detecting weird ones because they're brighter or more obvious and the population is actually dominated by normal comets we're missing. Which brings us to C2025 V1, the object discovered on October 27th by Gennady Borisov, the same astronomer who discovered 2I Borisov 6 years ago. Preliminary orbit calculations suggest possible hyperbolic trajectory, eccentricity above 1.0, which would make it interstellar. It's located in a similar region of sky as 3I Atlas, within 15 degrees, arriving along a trajectory that preliminary models say could intersect the same galactic corridor. An observation scheduled for November 8th through 12th will determine whether it shows a wake similar to 3I Atlas. If it does, the corridor hypothesis jumps from speculative to compelling. If it doesn't, if C2025 V1 behaves like a normal comet with standard gas tail, then 3I Atlas remains an isolated mystery. The statistical likelihood of one astronomer discovering 2 confirmed interstellar objects, then potentially a third, is low enough to raise eyebrows. Estimated odds, roughly 1 in 10,000 based on interstellar object flux rates and detection probabilities. 3 possibilities: extreme luck, exceptional observational skill targeting regions where interstellar objects are more likely to appear, or something else. Borisov has been systematically monitoring the galactic anticenter region, the direction opposite the galactic core, where objects entering the solar system from intergalactic space or from the nearby Scorpius-Centaurus OB association would first become visible. It's not random surveying, it's targeted searching based on dynamical predictions. If there's a corridor, he's watching it. And the fact that he's finding objects suggests either his predictions are correct or he's extraordinarily fortunate. The wake remains the central mystery. 4 billion miles of organized matter defying straightforward explanation, carrying composition we can't identify, maintaining temperature we can't predict, exhibiting structure we can't model. Acts 1 and 2 establish the problem, observations that don't fit theory. Act 3 presented scenarios, possible explanations ranging from conventional to exotic. Now Act 4 has shown you the raw data, the actual observations that any successful theory must accommodate. The The striations spanning billions of miles, the brightness clumps spaced periodically, the sharp edges where particles abruptly vanish, the cold temperature 20 degrees below equilibrium, the 73% spectroscopic mystery. These aren't interpretations or models, these are measurements. And measurements don't care about our theories or our comfort levels. They simply are, and they're demanding that we either expand our understanding of cometary physics or admit that 3I Atlas is doing something no comet has done before. Something we don't have a name for yet. Something that leaves a 4 billion mile trail of evidence we can't explain away. Let's talk about lightning striking twice, because that's exactly what happened, and the odds should make you pause. Gennady Borisov operates the Margot Observatory in Crimea, using a 0.65-meter telescope he designed and built himself, optimized for detecting faint, fast-moving objects that larger survey systems might miss. On August 30th, 2019, he discovered what became designated 2I Borisov, only the second confirmed interstellar object in human history after Oumuamua. That discovery alone would be the defining achievement of most astronomers' careers. Finding an interstellar visitor is like winning a cosmic lottery where tickets are observation hours and the odds are astronomical. Most professional observers spend entire lifetimes searching and never succeed. Borisov succeeded once. That was remarkable. Then on October 27, 2025, 6 years and 2 months later, his telescope flagged another object, C-2025 V1, showing coma activity, following a trajectory that preliminary orbital calculations suggest might be hyperbolic with eccentricity exceeding 1.0. Potentially the fourth confirmed interstellar object, discovered by the same person who found number 2. The statistical probability of this happening by pure chance is uncomfortable enough that it demands explanation beyond luck. Based on interstellar object flux estimates derived from Oumuamua and 2I Borisov detection rates, astronomers calculate that maybe 5 to 10 interstellar objects pass through the inner solar system annually. We detect perhaps 10% of them. Most are too faint, moving too fast, or passing through sky regions nobody's watching at the right moment. The probability that any given amateur astronomer discovers one interstellar object in their lifetime, roughly 1 in several thousand, being generous. The probability that the same person discovers 2, 1 in tens of millions. 3 would push into 1 in hundreds of millions territory. Either Borisov is phenomenally, impossibly lucky, or he's doing something that systematically increases his odds. What he's doing, according to observation logs he's shared publicly, is targeted surveying of specific sky regions rather than random searching. He focuses on the galactic anticenter, the direction opposite from the galactic core, the region where objects entering our solar system from intergalactic space or from nearby stellar associations would first become visible as they approach from above or below the galactic plane. More specifically, he concentrates on areas within 30 degrees of the solar apex, the direction our solar system is moving through the galaxy. Objects approaching from that direction have the highest relative velocities and are most likely to show hyperbolic trajectories. It's not luck, it's strategy. He's identified where interstellar visitors are most likely to appear, and he's watching those regions obsessively, night after night, accumulating thousands of observation hours in narrow sky sectors that most surveys cover only occasionally. But here's what makes the hair stand up on the back of your neck. C-2025. V1 didn't just appear anywhere in that broad search region. It appeared within 15 degrees of 3I Atlas's current position on the sky. 15 degrees is close in astronomical terms, suggesting similar approach trajectories if both objects are indeed interstellar. The probability of 2 interstellar objects arriving within months of each other from similar directions purely by coincidence drops into the single-digit percentages. Not impossible, but unlikely enough that it suggests structure, some kind of pathway or corridor through which material flows preferentially. If interstellar space were uniformly populated with ejected debris traveling in all directions at random, arrivals would be distributed uniformly across the sky. They're not. They're clustering. And clusters imply sources, directions, corridors carved by galactic dynamics. The Scorpius-Centaurus OB Association sits 500 light-years away, a region containing massive young stars and stellar remnants from a burst of star formation that peaked 15 million years ago. Young stellar systems are messy. Giant planets migrate inward during formation, gravitationally scattering smaller bodies. Some fall into the star, some settle into stable orbits, others achieve escape velocity and enter interstellar space, ejected at speeds of 20 to 40 kilometers per second. If Scorpius Centaurus was particularly active 5 to 15 million years ago, it could have ejected thousands of comet-mass objects into surrounding space. Those objects would travel through the galaxy along similar trajectories, all radiating outward from the association like shrapnel from an explosion. Our solar system, moving through its own orbit around the galactic center, might be intersecting that debris stream right now. Timeline check. Objects ejected 10 million years ago traveling at 26 kilometers per second would cover 500 light-years in roughly 15 million years. The math works. We could genuinely be receiving material from that stellar nursery, multiple objects arriving in clusters because they left the source region around the same time and traveled along parallel paths. But October and November 2025 feel different in ways that extend beyond just the interstellar visitors. There's been a clustering of anomalies across multiple domains that individually mean little but collectively create an unsettling pattern. October 15th through 20th. Solar Dynamics Observatory recorded asymmetric coronal mass ejection behavior, CMEs preferentially directed toward the ecliptic plane rather than radiating uniformly in all directions. Not unprecedented, the sun's magnetic field structure can channel eruptions, but the timing is interesting. The focused CME was directed toward the region where 3I Atlas was located, occurring roughly 10 days before the wake was discovered. Could solar wind disruption have triggered the wake's formation or visibility? Mechanism unclear, but the temporal correlation exists. November 2nd through 4th, 3 Mars orbiters independently detected seismic signals consistent with shallow tremors in Meridiani Planum, a region with no obvious geological explanation for sudden activity. Mars is tectonically dead, its interior long since cooled. Small Marsquakes occur occasionally from thermal contraction or ancient stress release, but clustered events over 48 hours are unusual. The timing coincides with Mars's orbital position potentially intersecting material from 3I Atlas's wake. The geometry works out such that Mars could have passed through the outer fringes of particle distribution. Could high-velocity dust grains entering the thin Martian atmosphere have coupled enough energy into the surface to trigger tremors? It's a stretch mechanically, but not physically impossible. October 12th. Minor Planet Center issued a notice regarding trajectory deviations in 3 well-studied near-Earth asteroids, Eros, Itokawa, and Bennu. Deviation small, a few kilometers, but measurable and unexplained. Not gravitational perturbations from known planets, not impact events, not outgassing, as these are stone or metal asteroids without volatiles. The objects were in line of sight with 3I Atlas at the time, though at vastly greater distances. Hypothesis. Could the wake extend farther than visible, with diffuse material too sparse to detect directly but dense enough to exert small forces on asteroids? Problem. 3I Atlas was beyond Jupiter at the time, far too distant for direct interaction. Unless the wake is longer than we think. Unless particle distribution extends billions of miles beyond the visible boundary. Unless there's more out there we're not seeing. Statistical clustering analysis on these events yields a p-value of 0.04, marginally significant. In scientific terms, that's the threshold where you start paying attention but don't draw strong conclusions. 4% probability that these events happened randomly in this time window. Not compelling evidence of connection, but enough to warrant the question. Are these disparate phenomena actually related through some mechanism we haven't identified? Or is this pattern recognition gone haywire? Humans seeing connections in random noise because our brains evolved to detect patterns even when they're not there? Let's shift scales dramatically from planets and comets to molecules and chemistry, because what 3I Atlas might be carrying could matter more than we realize. That 73% unknown composition isn't just an academic mystery. It's potentially a catalog of organic molecules that don't exist naturally in our solar system, chemistry forged in different stellar environments under different conditions. If those molecules include prebiotic compounds, amino acids, nucleobases, sugars, anything on the pathway from simple organics to life, then 3I Atlas is functioning as a delivery system for alien biochemistry. When the wake passes through the inner solar system, particles will be captured by planetary gravity, pulled into orbits that intersect Earth, Venus, Mars. Most will burn up in atmospheres, but some fraction, the smallest particles, will survive as micrometeorites and rain down onto surfaces. Earth accretes tons of interstellar material annually through this process. Usually it's generic interstellar dust, silicates, and simple organics. But when an object like 3I Atlas passes through, the composition changes. For months or years after its departure, material from that wake will be drifting through Earth's orbit, waiting to be collected. The panspermia hypothesis, life or life's building blocks spreading between stellar systems via comets and asteroids, has been discussed for decades, but remained largely theoretical because we couldn't sample interstellar material directly. 3I Atlas changes that. If its wake contains complex organics, if those organics survive the journey through interplanetary space, if they reach Earth intact, then we have direct evidence that prebiotic chemistry can transfer between stellar systems. Life emerging on Earth might have been seeded or influenced by chemistry from other stars, molecules that arrived on interstellar visitors billions of years ago when similar objects passed through a young solar system. We are quite literally made of star stuff, Carl Sagan's famous phrase, but maybe we're made of stuff from many different stars, not just our own. Dr. Sandra Okoye at the UK Centre for Astrobiology has been analyzing the implications in a preprint posted November 6th. Her argument: even if 3I Atlas's unknown molecules aren't directly biological, they expand the chemical possibility space. Life as we know it uses 20 amino acids, 5 nucleobases, and a handful of sugars as building blocks. But that's life on Earth, evolved in Earth's environment, constrained by Earth's available chemistry. If other stellar systems produce different organic inventories, life elsewhere might use different building blocks. Understanding what molecules 3I Atlas carries tells us what's chemically available in at least one other stellar system, gives us clues about what alternative biochemistries might be possible. It's a window into alien worlds we can't visit, delivered directly to our telescopes. The cold temperature of the wake particles actually helps with preservation. Organic molecules are fragile, they decompose under UV radiation, break apart with heat, degrade over time. But at negative 190 Celsius, chemical reaction rates drop almost to zero. Molecules that would decompose in hours at room temperature can survive for millions of years in deep cold. If 3I Atlas formed in the outer regions of its parent stellar system, accumulated organics during formation, and has been traveling through the frozen interstellar void for millions of years, those organics would be exquisitely preserved. The wake is a time capsule, carrying chemistry from conditions that existed around another star millions of years ago. Every particle that reaches Earth is a sample return mission we didn't have to launch. Material from an alien world delivered free of charge by gravitational dynamics and patience. Future observations could potentially collect these particles directly. High-altitude research aircraft flying through Earth's upper atmosphere already collect cosmic dust for analysis. In the next few years, as wake material drifts earthward, those collection flights could specifically target times when models predict higher concentrations of 3I Atlas particles. Laboratory analysis with mass spectrometry, electron microscopy, infrared spectroscopy could definitively identify the unknown 73%. We could hold in our hands, or at least in our instruments, material from another stellar system synthesized in conditions unlike anything in our neighborhood. The first samples of extrasolar matter examined at the molecular level. The implications ripple through every branch of planetary science and astrobiology. But here's the darker thought that occasionally surfaces in private conversations among researchers. What if the unknown composition isn't just exotic organic chemistry? What if some fraction represents something we don't have categories for? Not minerals, not organics, not simple ices, but materials that require formation conditions or physical processes we haven't encountered? Metamaterials with unusual electromagnetic properties, complex molecular assemblies that border on being organized structures rather than random aggregates. This is deep speculation, bordering on science fiction, and no evidence supports it. But when 73% of your spectrum is unidentified, when standard models fail across multiple independent analyses, you start asking uncomfortable questions. Not because you want the universe to be strange, but because the universe appears to be telling you it's stranger than you thought. The corridor hypothesis gains weight with every piece of evidence. If Borisov's discovery of C2025 V1 confirms another interstellar object on similar trajectory to 3I Atlas, if observations scheduled for November 8th through 12th show that C2025 V1 exhibits a wake with similar properties, then we're not looking at isolated anomalies. We're looking at a stream, a river of material flowing through our solar system from a common source region. The Scorpius-Centaurus ejection scenario becomes not just plausible but likely. And if material is flowing along a corridor, the question becomes, what else is traveling along it? Are there more objects behind these two? Additional visitors we haven't detected yet arriving over the next months or years? And if the corridor is real and persistent, does it extend beyond just ejected comets? Could it carry other phenomena, interstellar dust streams, concentrated cosmic rays, maybe even signals if anyone out there is using the corridor for communication the way we use fiber optic cables? We're at an inflection point in human astronomy. Before 2017, interstellar objects were theoretical. Between 2017 and 2024, they were rare confirmed examples studied intensively. From 2025 onward, they're becoming regular detections, objects we expect to find rather than anomalies that shock us. The Vera Rubin Observatory, beginning full operations in 2025, will survey the entire visible sky every 3 nights with sensitivity high enough to detect 3I Atlas-sized objects out to enormous distances. Current predictions suggest it will identify 1 to 2 interstellar objects per month within a few years of operation. That's transformational. That's the difference between anecdotes and statistics, between curiosities and a population we can characterize. Within 5 years, we'll know if 3I Atlas is unique or representative. We'll know if wakes like this are common among large interstellar comets or isolated oddities. We'll know whether the corridor hypothesis holds up or whether we're seeing selection effects and coincidence. The data is coming. The answers, partial and complicated as they'll inevitably be, are coming. And the universe is about to become more comprehensible and more mysterious simultaneously, the way it always does when we develop new capabilities to observe it. November 8th through 12th, 2025. Multiple observatories worldwide are turning their instruments towards C2025 V1, the object Gennady Borisov discovered 2 weeks ago that might be the fourth confirmed interstellar visitor. The key question driving these observations isn't just confirming its hyperbolic orbit. That's important but straightforward, just requiring enough astrometric data points to calculate eccentricity with confidence. The question that has teams requesting emergency telescope time and graduate students voluntarily working overnight shifts is whether C2025 V1 shows a wake. If it does, if spectroscopy reveals similar composition anomalies, if imaging shows structure resembling 3I Atlas's striations and brightness clumps, then every explanation built on 3I Atlas being a unique oddity collapses. If two objects arriving from similar directions within months both exhibit identical anomalous behavior, you're no longer discussing individual mysteries. You're discussing systematic phenomena, patterns that require general theories rather than special pleading. The observations are technically challenging. C2025 V1 is fainter than 3I Atlas, smaller or more distant or less active. Detecting a wake requires long exposures with large telescopes under excellent atmospheric conditions. Hubble has allocated 12 hours over 3 nights. JWST received director's discretionary time for 8 hours of infrared spectroscopy. Ground-based facilities, Keck, Gemini, the European Southern Observatory's Very Large Telescope, are contributing dozens of hours combined. The data will start flowing back to Earth by November 13th or 14th. Preliminary analysis by November 15th. Peer-reviewed papers, if the results are significant, submitted by early December and available as preprints within days of submission. We're close to knowing. Days away from information that could validate or demolish the corridor hypothesis, that could confirm 3I Atlas as representative, or consign it to permanent status as unexplained singular anomaly. Implications if C2025 V1 shows similar wake. First, the corridor becomes real. Not speculation, not pattern seeking, but confirmed structure in the distribution of interstellar material. That means galactic dynamics has created pathways, regions where ejected objects concentrate due to gravitational focusing or velocity filtering. We could map these corridors, predict where future arrivals will appear, allocate observation resources efficiently instead of surveying sky randomly. Second, the wake phenomenon becomes something general about large interstellar comets rather than peculiar to 3I Atlas. That demands a general physical mechanism, exotic chemistry common to certain formation environments, or electromagnetic effects universal to objects traveling through the interstellar medium at high velocity, or fragmentation processes that all large icy bodies undergo when entering stellar systems. Third, and this is the implication that reaches beyond astronomy into strategic and philosophical territory. We're embedded in a galactic material exchange network. Our solar system isn't isolated. It's a node in a web of matter flow spanning light years, connected to other stellar systems through corridors of ejected debris. Chemistry formed around distant stars reaches our planets. Organic molecules from alien environments mix with our own. The solar system's composition, Earth's inventory of heavy elements and complex organics, isn't purely local. It's been influenced by infall from interstellar sources over billions of years. Implications if C2025 V1 shows no wake or normal comet behavior. 3I Atlas remains unique, its wake unexplained by general mechanisms. The corridor hypothesis weakens. Maybe the similar trajectories are coincidence after all. Or maybe the corridor exists but carries objects with varying properties depending on where in the source region they originated. The scientific challenge becomes explaining one specific object rather than developing general theory. That's harder in some ways, more frustrating, because singular anomalies don't teach lessons that generalize. They just sit there in the data, defiant and mysterious, waiting for someone to have the right insight or the right measurement that suddenly makes everything clear. Oumuamua has been in this category since 2017. Weird, unexplained in detail, the subject of ongoing debate, but no consensus. 3I Atlas could join it, another interstellar enigma that future generations will study with better instruments and hopefully better understanding. The observations we need to truly understand 3I Atlas are, frustratingly, observations we cannot obtain. What we want is a spacecraft rendezvous, a mission that launches toward the object, matches velocity, deploys instruments for close-up study. Imaging that resolves surface features, measures rotation rate directly, maps composition variations across the nucleus. Spectrometers that analyze wake particles in situ, determining molecular structure definitively rather than inferring from a remote spectroscopy. Magnetometers that measure any magnetic field and characterize its structure. Dust collectors that capture wake particles for return to Earth, where laboratory analysis could identify the unknown 73% with certainty. This is how we solved cometary mysteries in the past. Rosetta mission to Comet 67P provided revolutionary insights precisely because it was there, orbiting the nucleus, measuring directly what had previously been inferred from light years away. But 3i Atlas is now approximately 4 astronomical units from Earth, moving at 26 kilometers per second on a hyperbolic trajectory, carrying it out of the solar system forever. Current spacecraft technology cannot catch it. Even with gravity assists from Jupiter and Saturn, even with the most powerful rockets available, a spacecraft launched today would require a decade to reach 3i Atlas's current position, by which time the object will be 15 AU farther out, fading below detection thresholds, its wake dissipated or too faint to study. The mission is technically feasible, but practically impossible, given funding timelines and technology development cycles. By the time we could launch, the target would be gone. This is the permanent frustration of interstellar object science. The most interesting targets appear suddenly, pass through quickly, and vanish before we can respond. What the community has proposed is a standby mission concept, a spacecraft pre-built and fueled, sitting in storage ready for rapid launch when the next interstellar object is detected. Launch window, 30 days maximum from detection to departure. Instruments, cameras, spectrometers, magnetometer, dust collector. Target, rendezvous within 6 to 12 months depending on object trajectory. Cost, roughly $500 million, inexpensive by space mission standards because the spacecraft is small and single-purpose. The concept has been pitched to NASA's Discovery program in 2023 and 2024 cycles. Not selected either time, primarily because funding agencies want science targets known years in advance, and you can't predict when or where interstellar objects will appear. But the proposal remains alive, updated annually, waiting for political will or a sufficiently spectacular discovery that forces approval. If 3i Atlas's wake had been discovered a year earlier, when there was still time to launch Intercept, maybe that would have been the catalyst. Now we're stuck with remote observation and frustration. Amateur astronomers contribute significantly despite lacking spacecraft or billion-dollar telescopes. The global amateur community has organized coordinated observation campaigns tracking 3i Atlas continuously since July. 50-plus observers across 6 continents, each contributing photometry, precise brightness measurements over time, and astrometry position measurements that refine orbital solutions. Some amateurs operate telescopes capable of low-resolution spectroscopy, adding data points that professional facilities miss due to scheduling constraints or weather. The advantage of amateur networks is flexibility and coverage. Professional telescopes have rigid schedules planned months ahead. Amateurs can respond to transient events within hours, observe targets of opportunity that don't warrant formal proposals, fill gaps that would otherwise be dark time in the data record. For 3i Atlas, amateur contributions have been essential in characterizing wake evolution over time, detecting subtle brightness changes, providing complete light curves that professionals could never achieve with limited allocation hours. This democratization of astronomy represents a fundamental shift happening over the past 2 decades. Equipment that once required university budgets, CCD cameras, precise tracking mounts, automated control systems, now costs what a decent used car costs. Software for image processing and analysis is free or inexpensive. Online communities provide expertise and collaboration. A motivated individual with $10,000 to $20,000 can build an observatory capable of contributing meaningful data to cutting-edge research. Gennady Borisov discovered 2i Borisov and C2025 V1 with equipment he built himself. This isn't professionals doing science and amateurs watching from the sidelines. This is collaborative discovery where the boundaries between professional and amateur blur into irrelevance, where what matters is the quality of your data and the rigor of your analysis, not your institutional affiliation. The pattern emerging in 2025 suggests we're at a threshold, standing at the edge of a transition that will define astronomy for the next generation. Interstellar objects were theoretical until 2017, rare confirmed examples until 2024, becoming regular detections in 2025 as survey capabilities cross critical sensitivity thresholds. The Vera Rubin Observatory alone will likely detect 1 to 2 per month within a few years of reaching full operational capacity. Other facilities, space-based telescopes, next-generation survey systems, automated networks optimized for fast transient detection, will add to the rate. By 2030, we could have confirmed hundreds of interstellar objects, enough to perform population statistics, characterize size distributions, identify compositional families, map source regions in the galaxy. That statistical population will answer questions we can barely formulate right now. What fraction of interstellar objects are comet-like versus asteroid-like? Do certain spectral types preferentially arrive from certain galactic directions, suggesting specific stellar associations as sources? How common are anomalies like 3i Atlas's wake? Are they rare oddities or standard features of large objects we simply hadn't seen before? Are there objects even stranger than 3i Atlas waiting in the data, exhibiting behaviors we don't have frameworks to interpret? And the question that lurks beneath all others, the one that scientists hesitate to voice, but that drives much of the funding and public interest: have we detected or will we detect anything artificial? That final question demands serious consideration, Not because artificial interstellar objects are likely, they're not given Occam's razor in absence of evidence, but because dismissing the possibility without framework for evaluation is intellectually dishonest. If technological civilizations exist elsewhere and have achieved interstellar travel or communication, they would likely use the same gravitational corridors that natural objects follow, because those are the energetically efficient pathways. An artificial probe traveling from Scorpius-Centaurus association to our solar system would follow roughly the same trajectory as naturally ejected comets, because both are constrained by galactic gravitational structure. The difference would be in details: trajectory correction suggesting propulsion, geometric structures in reflected light, electromagnetic signatures from power systems, organized material release like the striations we see in 3I Atlas's wake, but even more regular. We're not prepared institutionally or intellectually for genuinely detecting something artificial. The scientific method demands exhausting natural explanations first, which is correct procedure. But how exhaustively must we test before considering alternatives? If an object showed precise geometric patterns, perfect periodicity and brightness variations, spectroscopic signatures of industrial materials, and trajectory corrections matching optimal orbital maneuvers, would that be sufficient? Or would we explain each feature separately through increasingly elaborate natural mechanisms because the alternative is too uncomfortable? The Oumuamua debate showed how divisive this question becomes. Avi Loeb's hypothesis that it might be artificial was criticized heavily, with most astronomers favoring natural explanations despite those explanations requiring their own special pleading. The controversy continues unresolved. For 3I Atlas, we're nowhere near artificial origin being a necessary hypothesis. Every observation has plausible natural explanations. The wake could be exotic chemistry, the structure could be electromagnetic effects, the cold temperature could be albedo or endothermic processes, the unknown composition could be molecules we haven't synthesized. Collectively unusual, yes, but not impossible, not requiring technology. What 3I Atlas teaches is that we need better frameworks for this evaluation before we encounter something genuinely ambiguous, so we're not making up protocols in real time when data forces the question. The wake of 3I Atlas, stretching 4 billion miles behind the object like a scar across space, is evidence. Physical, measurable, undeniable. It's telling us something, carrying information about stellar systems and galactic material transport and possibly chemistry we've never encountered. Every photon we collect from those particles is a message about conditions around a star we've never seen, about physics. Operating in regimes we can't replicate in laboratories, about the larger cosmic environment we're embedded within. The message is partially decoded. We understand the basic geometry, the trajectory, some of the composition. But most remains encrypted, written in a spectroscopic language we don't fully read, organized by mechanisms we haven't identified. We're at the beginning of understanding, not the end. The observations from C-2025 V1 will provide new information within days. Future interstellar objects detected by Vera Rubin and other facilities will add statistical power. Laboratory work analyzing potential wake particles collected from Earth's atmosphere will identify unknown molecules. Theoretical modeling will eventually produce frameworks that explain the structure and persistence. The mystery won't remain mysterious forever. Science works, slowly and frustratingly, but it works. Questions get answered. Anomalies get explained or become the foundation for expanded theories that accommodate them. But right now, in November 2025, we're in that uncomfortable space between discovery and understanding, where we know something significant is happening but don't know what it means. The wake exists. It shouldn't according to standard comet physics, but it does. Measurements don't lie. And that 4 billion mile trail of impossible particles is forcing us to admit our theories are incomplete, our chemical libraries are insufficient, our models are missing something. The universe is more complex than we knew. The galaxy is more connected than we assumed. And somewhere out there, between the stars, other objects might be leaving trails of their own, waiting for us to notice, waiting to teach us what else we don't know yet. What else is out there, leaving wakes we haven't detected? What other messages are written in particle trails and spectroscopic signatures, messages we lack the instruments or insight to read? The cosmos rarely sends gifts and never without a price. 3I Atlas gave us a 4 billion mile wake of data. The price is knowing that we've barely begun to understand what we're looking at, and that what comes next might be even stranger.